Yes, this question. Riser is designed so as to. Yes, how the riser is designed? Freeze after the casting freezes. Now see that I am showing here one riser. I am showing here riser. Just see, this is the riser and this is the casting cavity. This is the casting cavity. You see that the riser is continuously supplying molten metal. This riser is continuously supplying molten metal to the casting cavity. Yes. Then just see that as this and just see in the riser design topic, there is an important thing that the surface area of riser must be minimum. If the surface area of riser is minimum, then the heat transfer from the riser is less, and if the heat transfer from the riser is less, then it will solidify later. Means first this casting will solidify, and after then the riser, whatever the molten metal present in the riser may solidify. Means who is solidifying first? Casting is solidifying first. What is given here? Riser is designed so as to freeze after the casting freezes. Freeze after casting freezes, that is correct answer. And if the riser is going to solidify first, then how the riser can supply molten metal to the casting? Not possible. Hence, riser must be freeze after the casting freezes. Second, freeze before casting freezes. Freeze before casting freezes means second sentence is saying that first riser is going to freeze, means riser is converting into solid then casting. Wrong. Freeze at the same time of casting. In the worst situation, we can also say freeze at the same time of casting, means riser and this molten metal in the casting cavity both is going to solidify at same time. Yes, it is also possible. Then option C is also correct. And minimize the time of pouring. Minimize the time of pouring, that is not correct. There is no any relation of the time of pouring and this. Now see that you may ask, sir, this is not a multiple select question. If it is a multiple select question, then you can give the answer A as well as C. But it is not a multiple select question. Only one option you have to give. Then the best option is which one? Freeze after the casting freezes. Riser will freeze after the casting freezes. Then also I am cutting this option. Then correct option is A. If multiple select question is there, then you can go with the option C also, A and C, right? See next question. The contraction allowance. What is mean by that contraction allowance? You know that the shrinkage allowance, and that shrinkage allowance is also known as solid shrinkage, and that solid shrinkage is also known as contraction allowance. Just see the contraction allowance means the solid shrinkage or shrinkage allowance provided on the pattern and core boxes compensate for the following type of contraction. You can see that the option, you can see that the liquid contraction, solidification contraction, solid contraction, and all the above three type of contraction. But here what is given? The contraction allowance. I said you that contraction allowance means what? Solid contraction, solid shrinkage, or it is also known as shrinkage allowance. But just see that ABC option I will show you on the diagram. ABC option. Just see here. Just see, this is the stage 1, this is for option 1, this is the stage 2, and this is the stage 3. In stage 1, what is happening? The liquid is going to contract, then there is a liquid contraction. Stage 2 is solidification contraction. Solidification means liquid is converting into solid, and at point C we are getting solid, at point D we are getting solid. Means C to D also there is a contraction. But I said you that at point C we are breaking the mold and taking out the casted component. And then whatever the contraction is happening from C to D, it is in atmospheric condition, it is outside the mold only. Then just see all the option. Yes, the liquid contraction is stage 1, solidification contraction, here I am writing stage 1, solidification contraction stage 2, and solid contraction, that is what? Stage 3. Then the contraction allowance means what? Solid contraction. Contraction allowance means solid contraction. And this question is over here. Now see the question on chills. What is the main function of chill? And that main function the questions are asked in GATE exam. The directional solidification is the main function of chill. How the directional solidification? You can see that this is the L. This is the L-shaped casting, means this is the L-shaped cavity. Cavity means that empty space, and in that empty space we have to pour the molten metal. We have to pour, and these two risers are there. This is one riser and this is second riser. The two risers are there. Now what is happening? What is happening here? This we are using one chill block, chill, or we can say chill block also. Chill or chill block we are placing. And what is the work of that chill block? Why the chill block is using? For directional solidification. Directional solidification means it is taking the heat, it is extracting the heat from this area and it is throwing to the outside area. And this material, chill or chill block material we are using, which have high thermal conductivity. High thermal conductivity means it transfers the heat. Understood? Now see, the chills are used in mold too. Why the chills are used in mold? To achieve directional solidification. There is only one and one function of chill to achieve directional solidification, and that is given option 1. Reduce possibility of blowhole. Oh, reduce possibility of blowhole, guys. There is one defect which formed because of, if we are not using the chill material, then there is one casting defect. One hole is forming, but that hole is not a blowhole. Just see what happened. Just consider that here we are not using chill. Just consider that here we are not using chill. Yes, we are not using here chill. Just consider that. Yes, chill is not there. If the chill is not there, then what happened? If the chill is not there, then you can observe that this is the total molten metal, and you can see that the heat transfer from this area. Then tell me, this is the outside area, this is the inside area. Outside area has no problem, very easily the heat is going to transfer. But you can see that from here is also heat is coming. Just see, from here is also heat coming. Then in that area, the more hot region is there, more temperature is there. And in that area, why the more? Because from here also heat is coming, here is also heat coming, then this is the hot region. If the hot region is there, then the heat transfer is minimum in this area. When there is heat transfer, when there is a difference between system and surrounding is more, then there is more heat transfer. Now here, the easily heat can transfer, but in that area, and this is most problematic, means this area is most problematic. Then what happened here? The heat is not transferring from this area. Then you can see that some part is going to convert into solid. Just see, this part will convert into solid first. But when this part is converting into solid first, it is going to shrink and it requires the volume of molten metal. Then this riser is supplying the volume of molten metal. When this part is converting into solid, this part is also converting into solid. And when it requires the volume of molten metal, then this riser is supplying the volume of molten metal. Yes, but in that area, you know that the heat transfer is very less. In that area, that heat transfer is very less. And because after two region, this region 1, region 2, after two regions solidifies, this region is started converting into solid. And here we are not using that chill block. Consider we are not using chill block. Then what happened here? What is the case? When it is going to shrink, then it required extra volume of molten metal. Then who will supply? Even though we are using the two risers, but here it is converting into solid, then this riser can't supply molten metal to this area. Here also it is converting into solid, then how this riser can supply the molten metal? No one can supply the molten metal, and because of that, you can see that some empty space will create here, and that empty space is because of non-availability of molten metal. Non-available of molten metal, some empty space is creating, and that empty space is known as void. Void or shrinkage cavity. Void or shrinkage cavity. Void or shrinkage cavity. Now it is not saying as a blowhole. It is void means empty space or shrinkage cavity. Blowhole is some different things. If the air particle is entered, if the air is entered, air bubble is entered into that molten metal, then we are getting the blowhole. But here what is void or shrinkage cavity? Why the word is shrinkage cavity? Because of shrinkage, the cavity is produced. Cavity means because of shrinkage, empty space is produced. Yes. Now see, that correct answer is A. Reduce freezing times, smoothen the metal for reducing spatter, nothing. That correct option is option A. Now see some GATE previous year question on properties of molding sand. Yes, there are a number of properties of molding sand, that is the porosity is one of the property, strength, collapsibility is the property, cohesiveness, adhesiveness, then flowability, all are properties. Now see the question on that. Increase in water content in molding sand causes, increasing water content of the molding sand causes. Now see that while constructing the house, we are taking the silica sand. In that silica sand, we are adding the cement, and again we are adding the water. As the content or as the percentage of water we are increasing, then what happens? The flowability will increase. Yes, flowability will increase. There are two terms, one is fluidity and second is flowability. Just see, the while constructing the house, that mixture by the hand also you can spread that anywhere, or for the plaster purpose you can see that it can easily flowable. And the flowability is term used in case of solids, and the fluidity, this fluidity and fluidity is used in the cases of gases and liquids. Yes, same way as I said you the example of plaster or that mixture of sand, cement and water for constructing the house, here is also same. There is a mixture is there, mixture of silica sand, clay plus water is there, and from that mixture we can say that increase in water contains in the molding sand causes flowability go to go through a maxima, flowability to go through a maxima. And that again all that three options are very irrelevant option, not a relevant, because permeability to go through a maxima, no. Compressive strength to go through a maximum, what is relation of compressive strength and water content? No. Strength to go through a maxima, no, no any relation of the strength. Yes, then correct option is A. Now see, very interesting question. The pressure at the ingate will be maximum. Pressure at the ingate will be maximum with the gating system. You know that the area of a sprue as to area of runner as to area of ingate. Then where the pressure is maximum. Now see that here you can see that 1:2:1 means here the pressure is maximum. If the area is maximum, pressure is maximum. Concept of venturimeter in the subject fluid mechanics. In the venturimeter you can see that this is the section 1. Just see, I drawn the section 1. This is what? Section 1. Yes. Now this is the converging section. Now I am drawing here the sprue. Sprue is straight. This sprue is straight, and after then again diverging section. Yes. Now you can see that at the section 1:1 and this is the section what? 2:2. You can see that the velocity of second section is greater than velocity at first section. Yes, and the pressure at one section is greater than pressure at two section. Means where the area is bigger, the pressure is more. Then I can see that in the option D, the pressure is more for runner. The first is area of a sprue, area of runner, area of ingate. Then you can see the 2 is area of runner has more pressure. Here at the option C, you can see that area of ingate has more pressure, and that only here asked. The pressure at the ingate will be maximum with the gating system. Yes, here is the 4, but we need to check that all option. Then here 1:3:3 means area of runner ingate are same. And what about the here? Here what we'll do now, we will divide by 4. 4 then it is 1:2, it is 3/4. What is 3/4? 3/4 means what? 0.75. 0.75 means less. Then where? In option C only the maximum pressure is there. Now see this very interesting question. When there is a no room temperature change, the total shrinkage allowance on a pattern is independent of, what is the formula for shrinkage allowance? That is delta L change in length is equal to alpha delta T, that is the freezing temperature, minus room temperature into capital L. What is delta L? Delta L is the change in length, alpha is coefficient of thermal expansion, TF is freezing temperature, TR is room temperature. In the diagram you can see this is the freezing temperature, TF is the freezing temperature, and TR is the room temperature. Yes, you can see that this is the TR is room temperature, and you can see that here the capital L is given. Capital L is what? Original length of component. Original length of component. Now you can see that here, then you know that the solid shrinkage is the stage 3. Is the stage 3. Stage 3 from where? This is the point A, this is the point B, point C and point D. C to D is a stage 3. And at C there is a solid, at a D also there is a solid, then it is a solid shrinkage, and that formula is written here. Then what the question is asking? They are asking the shrinkage allowance, that is the total, they are asking the total shrinkage allowance is independent of. Yes, now you can see that shrinkage allowance means what? Delta L is depend on alpha. Here just see alpha is coefficient of thermal expansion, it depends on alpha. Then next, the component size. L is original length of component, that is original component size. It is directly proportional to. Wrong, because they are asking it is independent, they are asking. Next, freezing temperature of liquid metal. You can see that liquid metal, this is the freezing temperature. Delta L is directly proportional to. This is also going to cancel. Then what is final? The powering temperature. Just see, here is the powering temperature is written in this formula, not written. Hence the correct answer, it is independent of powering temperature of liquid metal. Yes, how easy question? Just see, this question is asked in GATE PI 90, and similar question, same question I can say they asked for the mechanical examination. You can see the GATE mechanical 91. Recently after 1 year they asked this question. There is no room temperature change. The total shrinkage allowance on a pattern is independent of. Same question is there. Answer is powering temperature of liquid metal. This question is over. Same question, everything is same. Options are also same. Answer is correct. Answer is A. Now see the next question. Just see old question. Converging passage is used to feeding the liquid metal into the mold. Just see the which converging passage we are using. You can see that this is the converging passage. This is the converging passage we are using. Converge. This is the converging passage we are using. Now see that why we are using that converging passage, that is one biggest question, and that question is the answer of this question. Yeah, why we are using the converging passage? You can see that if we are using the converging passage here, just see here we are using continuous converging passage, and because of converging passage what is happen, it is maintained, we can maintain the pressure here. Instead of converging passage, just see if we are using the straight sprue, this is the sprue, converging sprue we are using. Instead of that, if you are using the straight sprue, then what happen? Some pressure will reduce in this area. Pressure will reduce in this area, and if the pressure is going to reduce, that pressure will be lesser than atmospheric pressure, and then because of that, the atmospheric here will enter into that, enter from the mold to here, and will enter into the molten metal. Hence aspiration of air will take place. Means inhalation is there. Inhale means we are taking the air in, that is inhale. In the same way that aspiration, here also its sprue will also take the air from the atmosphere, and that air will enter into the molten metal, which will give the defect in casting. And whatever the air is entering, that effect is known as aspiration. Then to avoid this, we are using this converging sprue, and there is one of the derivation for that also is there. Derivation is also there. Then how here the pressure is going to decrease? You may have question. You can get your answer in the fluid mechanics subject, but still here I will explain how it is. In the fluid mechanics subject, there is a chapter flow through pipe. In that flow through pipe, you can see that there is sudden contraction. Just see the case of sudden contraction. This is the case of sudden contraction, and you can see that if you are rotating this case by anti-clockwise by 90 degree, then you will get the same case. Here what is happening? Here vena contracta is happening here. Just see here the flow is there, and again you can see that here the vena contracta is happening here. Area is here reducing. If the area is reducing means the pressure is also reducing. Here is also same case is happening. Pressure is going to reduce. That's why atmospheric air is entering into that. And to avoid this, if we are using, to avoid this vena contracta, if we are using this tapered sprue, like that tapered sprue, then we can avoid that vena contracta effect. We can avoid that vena contracta effect. Understood? Hence, the converging passage is used. This converging passage can avoid the vena contracta effect. Hence, the converging passage is used for feeding the liquid molten metal into the mold to avoid aspiration of air. And all the three options are not good options. Yes, that's why I am not going to explain that all. Increase in rate of feeding, they are saying anything. And to explain that all the option, it takes a lot of time. It is not required here already. In the while teaching, I explained that all the things, but here it was main concept. In a green sand molding process, uniform ramming leads to. Just see uniform ramming. Just see uniform ramming means here is one pattern. Here is one pattern. Yes, in green sand molding, this is one of the pattern, and on the pattern we are giving the sand. Everywhere we are giving the sand. After giving sand, we are compressing that sand. There are two methods to compress that. One is by human hand or by second machine. If we are giving the force by human hand, then what is the problem? The uniform ramming will not be there. But if we are using the machine, then the uniform ramming is there. Then what is the advantage of that uniform ramming? Uniform is from the all side we are giving the uniform pressure. All the side same pressure is there. Then what is the answer? The less chance of gas porosity, uniform ramming. Here the uniform ramming, they are telling that, they are not telling that high force, we are giving very high force, high strength, high hardness. If they are saying that high strength, high hardness, then there is a less chance of gas porosity, we can say. B, uniform flow of molten metal into the mold cavity. No. Greater dimensional stability of the casting, that is the correct answer. If we are giving the uniform ramming, then there will be the greater dimensional stability of casting. Less sand expansion type of casting defect. Yes, I already taught that what is that sand expansion defect. I taught in our recording, that is ACE Online is the app. This is the app. In that app there is a recording. In that I taught that sand expansion type of defect. Sand expansion means, just I will tell you also, when we are pouring the molten metal into the casting cavity, then there is an expansion of sand. Expansion of sand means what is happening there? Because of expansion of sand, the volume of cavity is going to increase. That is the expansion of sand. Okay. Now this is option, greater dimensional stability of the casting. Now see some theory question of GATE examination which is asked on centrifugal casting. Just see the centrifugally casted product have. Just see the centrifugally casted product, you can see that in the centrifugal casting, the mold is continuously going to rotate. Mold is continuously going to rotate, and as the mold is continuously going to rotate, it is throwing that molten metal. It is throwing that molten metal. Just see, it is throwing that molten metal. You know that by the centrifugal casting, we are going to manufacture the pipes. You see that we are going to manufacture the pipes. Just see here, this pipe we have to manufacture. Yes, then what is happening? The molten metal is throwing, molten metal throwing towards the outermost circumference. Like that, the molten metal is throwing towards the outermost circumference. And what is happening? Here is, just see, this is the yellow is molten metal, and I will draw here white color is mold. Just see that I am drawing here white color is the mold. You can see that white color is the mold. Now you can see that the mold has a contact with the atmospheric air, and that mold is going to rotate continuously, and because of rotation, the continuous at the outer side, the new air is coming in contact, new air. Yes, and it is continuously rotating. That's why what is happening? The fast cooling is going on. Fast cooling of molten metal is going on because here the forced convection condition is going to occur. Forced convection is what? Force convection is what? That is related to heat transfer subject, and because of that it is outside molten metal is cooling very fast, and the fast cooling leads to fine grain structure. The fast cooling leads to fine grain structure. Then the fine grain structure we will get. Fine grain structure means grain size is very small, and you know that if the grains are small, if the grains are smaller, then that smaller grains are high strength. The larger grains has low strength. This larger grain has low strength. You can see that this larger grain has low strength. Smaller grains, that is the fine grains, has high strength, and if the strength is more, you can see that the density is also more. Density is also more. Then the centrifugally casted product have fine grain structure with high density. Fine grain structure with high density. Now see again interesting question, that is light impurities in the molten metal. Light impurities in the molten metal are prevented for reaching the mold cavity by providing. Now you can see that these are three accessories used in gating system. What are the accessories? Just see, you are driving the bike. How many accessories for the bike? The helmet is accessory. The indicators are the accessory. Yes, that are the accessory in bikes. It is not mandatory. Even though we can say that the lamp is also accessory, we can say that. Without lamp, without indicator, without helmet, we can drive the bike, but it is not safe. Same way to remove the impurities. There is no need to use that all that three part, but it is better to use for a safety purpose to avoid the defects. And that accessories are strainer, splash core and skim bob are three accessories are present there. Yes, and out of that, which one, just see the strainer, bottom well, skim bob, which one is separating or prevented the light impurities, which one is not allowing the light impurities to enter into the casting cavity. Just see that as the molten metal is flowing from here, you can see that the molten metal is flowing. Just see as the molten metal is flowing, always the lighter impurities which will float at the top of molten metal, then what happens when it is flowing, the lighter impurities will stuck here at the top portion of skim bob, and the heavier impurities will stuck here. Heavier impurities will stuck. Then by this way, the lighter impurities, we can, these are lighter impurities in the molten metal as well as heavier impurities we can separate in the skim bob. Lighter at the top and heavier at the bottom. Then what is the answer? The answer is bottom well skim bob. Then answer is what? Skim bob. Now the next question, what is the bottom well? What they are saying about the bottom well? What is the bottom well? Just this is the bottom well. The lower portion of the skim bob is also called as bottom well. Bottom well. This is the what? Bottom well is there. Understood? Now the bottom well is separating the high density impurities. Yes, not a light impurities or lighter impurities. Hence only this is not correct. This is not correct. Then all of these is also not possible to. Yes, not possible to correct. And what is the strainer here? The strainer is also removing. Strainer can remove the both impurities, lighter as well as heavier impurities it can remove. But in the strainer, that the size of impurities must be bigger. Either it is low density or high density impurities. But if the size is bigger, then the strainer can avoid that. Yes, strainer can remove that. Correct. Now here the correct answer is what? Option C, that is skim bob is avoiding lighter impurities as well as heavier, but in the question lighter is asked, then skim bob only one of the answer. Now see the question on draft allowance. Disposable pattern is made of. Just see mechanical 2000 question. The disposable pattern are made up of. What is meant by disposable? Disposable means thrown away after being used. Just see if we are using the polystyrene pattern. Just see if we are using the polystyrene pattern, then what happen? In the casting cavity, you can see that the polystyrene pattern is remain there in the casting cavity. Just see, if it is a casting cavity, then you can see that the polystyrene pattern is remain there. Polystyrene pattern is remain there. And do you know that we are directly powering the molten metal? We are directly powering the molten metal here. And when that molten metal is touches to that polystyrene, just see this is the total the polystyrene, then what happened? That polystyrene is melted, means melting of polystyrene is there and evaporation of polystyrene there. Hence here the polystyrene is melting and evaporating, and evaporated polystyrene will go outside the mold through the porosity property of mold. Through the porosity property of mold, you can see that through the porosity property of mold. Yes, then and that what are the polystyrene going out through the mold, it cannot be possible to collect. Hence we are saying that disposable pattern is made up of polystyrene, because once it is used, it is not possible to use it again. Hence it is the disposable pattern. Now see, very easy question. To cubical casting, the cube shape is given. To cubical casting of the same metal and sizes of 2 centimeter side and 4 centimeter side. Just see the first, the 2 cubical casting, first size is 2 centimeter side. The second is side is what? 4 centimeter. Are molded in a green sand. If the smaller casting solidifies in 2 minutes, smaller casting I am writing here tau 1 is solidifies in 2 minutes, the expected time for solidification of larger casting will be how easy? Just see here I am writing tau 1 by tau 2 is equal to m1 by m2 whole square. Tau 1 is 2, tau 2 is equal to m1. Now what is that m1? How to calculate that m1? Just I am writing here modulus of 1, that is a1 cube divided by 6 a1 square, means for cube volume divided by surface area. What is modulus? Volume divided by surface area. Then you can see that it is a1 by 6. Then modulus of 2 is equal to again a2 cube divided by 6 a2 square. Then you can see that this is the a2 by 6. Now we have the value of a1 and a2. What is a1? 2. Then I can write here 2 by 6, and here we can write that 4 by 6. Now see here m1. What is m1 now? m1 is 2 by 6 and m2 is what? 4 by 6. 6 get cancelled. 2 by 4 whole square. Now see here the 2 by tau is equal to, this is 2, this is 4, 1 by 2 whole square, 1 by 4. You can see that the tau 2 is equal to 2. 2. What is 2? Tau 2 is equal to, not 2, 4 into 2, 8. Tau 2 is equal to 8 minutes. Tau 2 is equal to 8 minutes. To see the answer, tau 2 is equal to what? 8 minutes. This question is over. You now see this question, match the following, all are the casting processes are here, and product we have to see which product we can manufacture. First is the slush casting. Slush casting. What we can manufacture from the slush casting here? Yes. Now see the lampshade we can make by, we can made that lampshade by slush casting. Answer is A4. Answer is A4. I am directly writing here answer A4. A4. Then shell molding. In that shell molding, we can manufacture that cylindrical block. Simple shape block we can manufacture by shell molding. Hence, I am writing the 3. Then dry sand molding. Dry sand molding and centrifugal casting. Now here you can see that the rainwater pipes, that pipes are made by centrifugal casting, then this answer is D5. Now there is big question about the dry sand molding. Is we are making the turbine blade, machine tool blade or cast iron shoe brake. Then by using dry sand molding, we can use that cast iron shoe brake. That is answer is what? 6. You can see that here the A4, B3, C6 and D5. These are all correct options. Now see, only 4 pairs can be matched here. Just see the investment casting. Yeah, no option is not given here. That our old question, they didn't give the option. The investment casting, what is the investment casting where we can use? We know that it is very easy that turbine blades can be made by investment casting. I am writing A2. Then die casting, the die casting, where the die casting is used. Now see, there are 2 type of die casting is there. One is gravity die casting and second is what? The pressure die casting. And in the pressure die casting, we can use the carburetor of IC engine. And then B6, by the pressure die casting, we can make the carburetor of IC engine. How many options are over? The turbine blade is over, carburetor is over. How many going to match? Only 4 pairs can be matched. Next, centrifugal casting, very easy, the cast iron pipes. Cast iron pipes are made by centrifugal casting. This option is also over. Then drop forging, very famous, the connecting rod is made by forging process, hence answer is 3. By forging process we can manufacture connecting rods. Next question. Here is also there is no option. Sand casting, plaster mold casting, shell mold and investment. Number of options are given. Now you can see that for the investment casting, the parts have hardened skin and soft interior for the investment casting. Yes, but just see one by one, we'll see the sand casting. In the sand casting, the part have a tendency to WARP. Warp means warpage is there. Warpage is there. The parts can bend. How that parts can bend? Yes, you can see that there are 3 stages of casting, 3 stages of cooling of casting. After stage 2, we are taking that casted component along with mold. And we are started breaking that mold. But because of vibrational forces, some of the casted component may also bend because it has high temperature, it is not at room temperature. Bend means what? Warpage is there, then A is 5. Then plaster mold casting, the plaster mold casting, you can see that the answer is minimum post casting process 3. Why it's so? You say that in the plaster mold casting, on the pattern we are pouring the plaster and waiting for solidify. After solidification, again in the furnace we are giving that heat to the plaster. Yes, and the plaster is very nice surface finish on that, very smooth is there, very nice surface finish on that. And here hence we are getting the very accurate component. In the post process, that is post casting process, that is machining, can be avoided when we are using the plaster mold casting. Now next, that is the shell mold casting. The shell mold casting, the very symmetrical and circular shape parts we can manufacture by shell mold casting. And investment casting, you can see that part have hardened skin and a soft interior. Because in the investment casting also, when we are pouring the molten metal, then you can see that the solidification is very fast at the outer edge. Yes, the heat transfer will be there from the outer edge of that component. Hence, because of fast heat transfer, the parts have hardened skin and soft interior. Why it happening? Sometime in the investment casting, we are using the mold of cement concrete, and cement concrete has high thermal conductivity. When we are using the cement concrete as a mold material, then fast heat transfer is there, and because of fast heat transfer, the parts outer edge is very hard, but the interior requires some time to cool. More time is required for cooling. Hence, at the inner side there is soft material is present. Hence, here the answer is part have hardened skin and soft interior too. This question is over. Now see the first theory questions here. Penetration is increased by. Penetration means what? Penetration means what? there is a workpiece, if there is a workpiece here, just see, if this is the workpiece and here the welding is done, then this is known as penetration. This is known as penetration. Then that penetration can be increased by, how that penetration can increase? To increase that penetration, the large amount of heat we need to supply. How we can give the large amount of heat? Means heat generation must be high. Then heat generation must be high. Then for that, what we can do? We can increase the welding current. We can increase the welding current. Yes, we can increase the welding current. Here is also you can see the option increasing the welding current. We have to increase the welding current, but decreasing welding speed. But we have to reduce the welding speed. Now, what is meant by welding speed? Welding speed means you can see that electrode is here and that electrode is supplying molten metal and electrode is moving along the length of weld bit like that. Then if we are reducing the welding speed, means electrode is moving very slowly, then electrode is supplying large amount of heat. We are giving the current, we are increasing the current here and we are decreasing the welding speed. Then electrode is moving with very small speed, and because of that, at the tip of electrode, the large amount of weld pool is going to form. Weld pool means what? The pool of molten metal is going to form, and the depth of penetration also we are getting greater. And correct option is option B. It can be increased by increasing the welding current and decreasing the welding speed. Always you need to remember that. What is meant by welding speed? That is electrode moving speed along the length of plate. Yes, next question. At a small variation of arc length, at operating condition, the manual metal arc welding transformer provide nearly. Manual metal arc welding means SMAW, which is very old process. SMAW, and that SMAW is known as shielded metal arc welding, and that method is manual and that is very old method. Then shielded metal arc welding, we just consider that this is one of the electrode. This is one of the electrode and that electrode is coated with some coating. Yes, then this is known as shielded metal arc welding. Means when the arc is going to develop, this electrode, tip of electrode is melting and it is supplying the molten metal. But this electrode, the coating is given on that electrode, hence the electrode is also melting, the coating is also going to melt, and electrode molten metal plus coating molten coating is entering into the weld pool. Then at a small variation of arc length, at operating condition, the manual metal arc welding transformers nearly. Yes, manual metal arc welding transformer provides nearly constant power or constant current or constant voltage, that we have to see. Now see that manual metal arc welding means shielded metal arc welding. Here one welder is working there. Here the machine is not there. Welder is working there. Welder is working there. And as you know that this is the L value. L is means what? Arc length. Guys, as this arc length is increasing means what is happening? The distance between this tip of electrode and workpiece is going to increase. As the arc length is going to increase, then what happen? As the arc length is going to increase, then what happen? Here the voltage also increases and current reduces. And when the arc length is going to reduce, then voltage is also reduces and current is going to increase. Means as the arc length is going to change, that values are going to change, guys. When the welder is working, just you or me is working there, then it is very difficult for us to maintain that distance because of vibrations of human head. It is very difficult for us to maintain that distance. It is very difficult for us to maintain that same value of arc length. Just see if it is a 2 millimeter value, guys, see how small that 2 millimeter value. That is this possible for you or me to maintain here the 2 millimeter distance? The distance will always change, 2.5 millimeter, 3 millimeter, 1 millimeter, is like that. Or sometime by mistake that can also touch to that plate also. and hence the arc length is going to change, then the voltage and current both value are going to change. And if the current is going to change, then heat generation is going to change, and that's why even though the arc length is changing, we need to give almost same current, because the heat generation is equal to I square R. Heat generation is equal to what? I square R. Yes, then if the current means heat generation is totally depend on current, and that's why we need to give the such a type of power supply in which the current remains constant. And current, it is very difficult to maintain constant current as arc length is going to change, but almost constant will be there. If the current is changing, very small value of current can change. Hence here the manual metal arc welding transformers provides nearly constant current. Now next, for gas welding a particular job using neutral oxyacetylene flame, the acetylene consumption was 10 liter. In a gas welding a particular job using a neutral oxyacetylene flame, in that question they mentioned that this is a neutral oxyacetylene flame they mentioned in this question. And even though they are not mentioning neutral oxyacetylene, only if they are telling only oxyacetylene flame, then only we are taking neutral flame. The acetylene consumption was 10 liter. The oxygen consumption from the cylinder, again a neutral flame, then I am writing O2 to C2H2 is equal to 1. Then if the acetylene consumption is 10 liter, then the oxygen is also 10. Then I am writing correct option is option B. Correct option is option B. Now in the resistance welding, you can see the first question here. For resistance spot welding of 1.5 millimeter thick steel plate, what is the thickness? 1.5 millimeter thick steel plate. The current required is of the order of what the current required. Just see, if the thickness of the plate is 1.5 millimeter, and if it is a steel plate, then fixed value is 10,000 ampere. Then the fixed value is what? 10,000 ampere. It is a fixed value. 1.5 millimeter steel plate, it is 10,000 ampere. But instead of steel, if the thickness is same but the plate is aluminum, then answer will be different. If the plate is steel but thickness is not 1.5, if the thickness is going to change 3, 4, 5 millimeter, then also the current will be different. That you need to remember. In an explosive welding process, the maximum velocity of impact, here we need the maximum velocity of impact is fixed by the velocity of sound in the flyer plate material. Now there are two plates in that. This first plate which is flying is known as flyer plate, and the second plate is known as backer plate or target plate. Then what happened? Some piece of metal we kept to support between the two plates, and on the top plate, means on the flyer plate, we are giving some rubber layer first here, and above the rubber layer we are providing some detonation here, some material here, then some material here. Now you can see it here, when we are here, the some material is there, and on that material, if we have to just see some fire we need to give that material, then what happened? The very big blast is there, and because of that big blast, this top plate is known as flyer plate, and this is the target plate. The flyer plate suddenly will go down with the high velocity and it will hit on the target plate. Then whatever the to keep the some distance between the two plates, some metal pieces are kept, and that metal pieces, the deformation, complete the plastic deformation of that metal pieces will happen, and that metal pieces, some part of that metal pieces in add in top plate, and some part of that metal pieces will add in bottom plate. Bottom plate is what? Target plate. And in a such way that we will get the two plate here, two plates here, yes, two plates, and here you can see that in the two plate some layer we will get. You can see these two plates are there. The bottom surface of this flare plate and the top surface of this target plate. The material of the bottom of the flare plate, the material of the top of that target plate will mix into each other and some waviness will form at the joint. Yes, next. In DC welding, the straight polarity results in. There are two types of power source. One is alternating current and second is direct current. And in the direct current, the two cases are there. In that one case is the more heat is going to generate at workpiece. It is known as direct current straight polarity. Yes, here you can see that the electrode is connected to negative terminal and workpiece is connected to positive terminal. And this is known as direct current straight polarity. And here also it is written the direct current straight polarity means electrode is connected to negative terminal. Yes, results in lower penetration, lower deposition rate, less heating of workpiece, smaller weld pool. Just see that this is the direct current straight polarity, and where there is a positive sign is there, here the heat generated is 2/3 of heat generated, 2/3, and here only 1/3 of heat generated. Here it is a 2/3 of heat generated at the workpiece, then large pool of molten metal will develop at workpiece because the more heat is generated here. Then you can see that what is option with straight polarity result in smaller weld pool. Wrong. Large weld pool will develop here. Next, less heating of workpiece. Wrong. More heating of workpiece because more heat is generated at workpiece with the straight polarity. Lower deposition rate. What is meant by deposition rate? The electrode is supplying the molten metal, that is known as deposition rate. And here the less heat is generated at the electrode, less heat generated at the tip of electrode, hence the electrode is supplying less volume of molten metal. Electrode is supplying less volume of molten metal. Yes, and if the electrode is supplying less volume of molten metal means lower deposition rate, means in DC welding with straight polarity, lower deposition rate. Next, lower penetration, that is wrong. Lower penetration means what? Here, this is the penetration, large depth. Yes, but here, straight polarity result in lower penetration. What they are telling? Here the lower penetration. Now you can see that more heat is generated at workpiece, and because of that more heat generated at workpiece, here is not lower penetration, here is deeper penetration is there. Deeper penetration. Hence lower penetration is also wrong answer. Then correct is only lower deposition rate. Now see next question. The electrode used in arc welding are coated. This is not expected to. In the arc welding we are using coated electrode and this is not expected to. Why we are giving the coating? We are giving coating to provide protective atmosphere to the weld. Correct. This is the correct. Stabilize the arc. For stabilization of arc purpose we are using the coating on the electrode. To add alloying element also we are using the coating, but we are not using coating to prevent electrode from contamination. Yes, what is the question? The electrode used in arc welding are coated. This is not expected to. Correct answer this. Prevent electrode from contamination. This is not expected. Option D is not expected. All A, B, C are right. Not expected. This is not expected. And now see also the number of questions asked for gate, mechanical as well as PI. Now you can see that this question, very old question, gate mechanical 94, they asked for 1 mark. What is the question? The ratio of acetylene to oxygen is approximately for neutral flame used in gas welding. Now you can see that there are number of flames we are using in the gas welding. O2 to C2H2 means oxygen to acetylene ratio is 1 and it is for neutral flame. Neutral flame means the ratio is equal to 1, and what they are asking, the ratio of acetylene to oxygen is approximately, oxygen to acetylene is 1, means acetylene to oxygen is also 1, then the ratio of acetylene to oxygen is approximately 1 for neutral flame used in gas welding. Yes, neutral flame used in gas welding.
Right. Here is a question from welding topic asked in mechanical 1994, one more question. The question here it is, generally cylindrical parts are produced by powder metallurgy, should not have non-uniform cross section and length to diameter ratio exceeding. So suppose in a powder metallurgy operation, if the length to diameter ratio, if it is greater, very high, then you will not get a uniform cross sectional area. You will not get a uniform cross sectional area. So to get uniform cross sectional area here, for thin walled cylindrical tubes, for thin walled cylindrical tubes, for thin walled cylindrical tubes, okay, it is like this. Thin walled cylindrical tubes are like this, you can say, okay na? The length to diameter ratio must be nearly varying 2 to 2.5. So here length to diameter ratio, if it is exceeding 2.5, you will not get a uniform cross sectional area. Suppose thick walled tubes you can take, thick walled tubes you can take. If it is a thick walled tubes or thick walled cylinders like this, thick walled tubes or thick walled cylinders like this, then the length to diameter ratio nearly 4 to 5. Length to diameter ratio nearly 4 to 5. So here they are asking question for thin walled tubes, okay na? So generally you can take 2.5. But here clarity is not given, even is it thick walled tube or thin walled tube. If it is given, you should prefer. So if it is a thick walled tube 4 or 5, 5 maximum. If a thin walled tube, 2.5 maximum.
Preheating before the welding is done to make the steel softer. Why it's so? The preheating before welding is done. Just see what happened because of preheating. Just see, I am showing you here the two plate. This is the one plate and this is the second plate. Yes, the both plates are here. Yes. Now see, if you are doing the preheating in that region, then what happened? When the temperature is going in that region, then the transfer of heat is very slow. Transfer of heat is very slow. Because already here we are doing the preheating, here also we are doing the preheating. Means here is a high temperature, here is also high temperature, and that's why the heat transfer is very less. As because of less heat transfer, the slow cooling of weld bead is going to occur, and the slow cooling means annealing is there or normalizing is there, and because of slow cooling, this weld bead gets softer. Weld bead gets softer. If the preheating is not done, then what happens? Here the first heat transfer is there, and because of first heat transfer, some Martensite structure is going to form. Martensite structure. And that you know that martensite structure is extreme hard and brittle phase. Extreme hard and brittle phase. What the martensite structure is extreme hard and brittle phase is there, and to avoid that we need to do the preheating. If you are doing the preheating, then whatever the metal we are getting is not hard and brittle, very soft material we are getting, and that's why the preheating before welding is done to make the steel software. You can also see the other reasons are also correct. Yes, other reason means burn away oil grease is also correct, prevent cold crack is also correct, but most important to make the steel software or make the material softer is correct option. Prevent plate distortion, the prevent plate distortion, all are correct, but A is more correct. See, next question, welding process and heat source. The same type of question you can see, this question was asked in PI 90 and next same type of question asked for mechanical 91. The thermit welding. Again I am writing here for the thermit welding. A, that is exothermic chemical reaction 2. Then seam welding means resistance seam welding, then it is ohmic resistance. MIG welding is arc welding. Here you can see that electric arc is option. And friction welding is what? because of mechanical work. The same type of question they asked for mechanical. Last question they asked for PI, the same question is repeated. Now see the list 1 and list 2, welding of aluminum alloy, very famous method for aluminum alloy is the TIG welding. Then I am writing the answer of A3. Be ship welding means thick plates are there, and out of that all, which is the method of highest thickness plate? Means the highest thickness plate, you can see that in the submerged arc welding can be joined from 30 millimeter to 75 millimeter thickness of plate. Hence in the ship welding, I am writing for the ship building, the submerged arc welding is required. The joining of HSS drill bit to shank, friction welding is useful. Joining of HSS drill bit to the shank, we are joining that high speed steel drill bit to the shank by using the friction welding. Deeper penetration precision weld, electron beam welding. Why the deeper penetration is there? Then here 2, then A3, B1, C4, D2. Now you can see that in the electron beam welding, the electrons are focusing on a very small area, and the depth formed is also very good. Hence the answer is option 2. Deeper penetration precision weld is electron beam welding.
Question next one. So what they are saying is, if in a turning operation both feed rate and the nose radius are doubled, the surface finish value will be. Now what they are saying is, feed rate F2 when you compare with F1 it is double. Even nose radius R2 when you compare with R1 that is also doubled. Then what they are asking is,
What is the surface finish value? Whereas surface finish value H max, in the first case if you notice, it is F square by 8R. So you can write as F1 square by 8 R1, F square by 8R. Whereas H max in second case is actually F square by 8R again, but I am writing F square by F2 square by 8 R2. But here instead of F2 we can substitute 2 F1. So it will be a 4 F1 by 8 into R. So R is nothing but you can write 2 R1, 4 F1 square, 2 R1. Therefore, you can write here it as the 2 4. Therefore, 1 by 4th of F1 square by R it is. But I need 8 here. So if I put 8 as it is here, then you can write it as a 1 by 4 of F1 square by R1 only, but I need 8 also here. So 8 if I put here, so 8 will be in the numerator also. 2s are therefore double the H max of a first case. So you can say increases by 100%, right? Increases by 100%. H max double, no? Double means increases by 100% will be the answer for this particular question. Whereas it's a combined question of surface finish and the basic metal cutting. Whereas after this, if you look at this question, the ideal cutting fluid for low speed machining of metal should be one which, what they are asking is cutting fluid, that too for the low speed machining. So we know that whenever a tool is imposed to perform the cutting operation at low speed cutting, what happen? Chances of stickiness of the chip is possible on the rake face, whereas what they are saying is remove the heat faster from the cutting zone. You can say actual one of the purpose, but in low speed cutting forms a coating on the cutting tool by chemical reaction, never forms a low shear strength film on the work material at chip tool interface. You can say it is also one of the purpose. Serve as the dielectric, minimizing thereby reaction due to EMF at a interface. No, it is never be. So if suppose the same question was a newly introduced MSQ type, then we would have say option A and C both are possible. A and C both are answers if it is a MSQ, but it's a MCQ in an old previous paper. So among these two, if you look at the purpose of supplying cutting fluid at low speed cutting operation, basically you can say to dissipate the heat also, and due to supplying the cutting fluid, what happen is cutting fluid will react with the workpiece surface in low speed cutting. Whenever cutting fluid is reacting, especially impurities present in the workpiece surface, it makes the reaction and then forms low shear strength surface. So forms a low shear strength film on the workpiece material at chip tool interface. That helps to reduce the power consumption. Therefore, in these conditions, you can say answer is option C. Now next, crater wear always starts at some distance from the tool tip because at that point, see basically crater wear means when you look at the tool, a single point cutting tool after providing depth of cut and feed motion, there are two cutting edges. We have side cutting edge and end cutting edge, but majority of the side cutting edge involves in the orthogonal machining, right? So we can say that from the side cutting, from this particular side cutting edge position, 2 to 3 mm away, there is something called a heat affected zone. So this zone we call it as a heat affected zone. So this zone is at what distance means it is at 2 to 3 mm away from the cutting edge. So what happened? Crater wear always starts at some distance from the tool tip because here only majority of the crater wear on the rake face we notice it is because of heat affected zone. You can say maximum heat effect in the orthogonal machining will be there at that position. Cutting fluid does not penetrate, chip tool interface temperature is maximum, normal stress on the rake face is maximum, tool strength is minimum. Among all these you can say answer is option B in this particular case. So remember, 2 to 3 mm away from the cutting edge, there is something called heat affected zone. Therefore, always crater wear will be more due to maximum temperature on the rake face, as chip is continuously flowing over the rake face. That is one of the major reasons. Now, next, if you look at this question, most of the metal cutting heat goes into the, remember, in any conventional machining operation, we might be taking orthogonal machining as an example to represent, but in any conventional machining operation, as you impose the tool to perform the machining or to remove the unwanted material, among total heat, maximum will be carried by the chip, then the workpiece, then the tool. So even you can write a percentage sequence also, 75% of the total heat carried by the chip. In the remaining 20% will be carried by the workpiece and the 5% of the remaining heat carried by the tool. This is the decreasing order. So you can say that moving chip is carrying most of the metal cutting heat. Cutting tool, workpiece and machine tool, they are saying machine tool is actually holding devices, but we try to make the arrangement in such a way that maximum heat must be carried always by the moving chip only. That is one of the major purposes also, you can say, while doing analysis, or you can mention while arranging the tool for workpiece material machining, you make sure that always chip must carry maximum heat, so that it is anyway unwanted material. That is what our basic purpose. Now next, the effect of rake angle on the mean friction angle in machining can be explained by. See, basically when you engage the tool to perform the machining operation, after metal removal, chip flows over the rake face, right? So as chip flows over the rake face, this is what the zone. So shall I say, in this particular zone, initially large amount of heat is present between chip and the rake face, so that you can say that there is always a sticking. But by the time chip is flowing over the rake face, then heat dissipation occur, then slipping, or you can call it as the sliding, will begin between chip and the rake face. Therefore, you can say sticking then slipping friction model is always the standard friction model present between chip and the rake face of the tool. Therefore, answer is option B in this question. Whereas if you look at this question, cutting power consumption in turning can be significantly reduced by. See, basically in any conventional machining operation, not only turning, when you talk about any conventional machining operation, cutting power is nothing but cutting force into cutting velocity, right? Force into velocity. Whereas in any given turning operation, cutting power consumption reduces by increasing the rake angle of the tool, they are saying. You can say it is also one of the reason why, because frictional power reduces. And you can write instead of cutting force into cutting velocity, the cutting power, that is what the total power is, a summation of shear power and the friction power. The friction present between chip tool interface we must overcome. Therefore, you can say that increasing the rake angle of the tool reduces the friction, so frictional power reduces. Increasing the cutting angle of the tool, there is nothing called cutting angle of the tool, so option B is ruled out. Widening the nose radius of the tool, when you widening the nose radius, then what happens is problem of heat generation increases, that will increase the friction, that is never be a solution to reduce the power consumption. Increasing the clearance angle, if you increase, just it helps to avoid the rubbing, no use at all. That too, it reduces the strength also. Therefore, you can say among all these options, we can mention frictional power. If you reduce, that helps to reduce the total cutting power also. That frictional power reduces by increasing the rake angle of the tool. Therefore, answer to this question is option A. Built up edge is formed. BU is nothing but built up edge. So built up edge formation occurs on the wedge shape of the tool. So this built up edge is formed while machining ductile material at high speed cutting, ductile material at low speed cutting, brittle material at high speed cutting, brittle material at low speed cutting. Remember, all workpiece material we are classifying into two categories only. Either it is ductile or it is a brittle. Therefore, built up edge formation we are noticing only in case of ductile workpieces, and that too ductile workpieces at low speed cutting, there is a sufficient time available between chip and the tool to get the built up edge formation. At high speed cutting, there is no sufficient time. Therefore, the answer to this particular question is ductile material at a low speed cutting. So that is what answer to this question. So with this, few of the question we completed. Next, we'll go further for the solution of few more previous year questions.
Pure metal pose machinability problem in turning operations. The reason is, see, pure metal, the post machinability problem. Generally, pure metals you can take compared to alloys, pure metals have more ductility. Because of that more ductility, continuous chip is going to be formed. Okay, na? That is one of the drawback, continuous chip with build-up edge. See, first option is given, increased length of contact due to the production of continuous chip, susceptibility to chemical reaction, tendency to form intense adhesion joint with the tool face, absence of inclusions which aids chip formation. So, increased length of contact. So, for a pure metal has high ductility. Because of high ductility, remember, pure metal has high ductility. Because of that high ductility, okay, continuous chip is going to be generated. So that length of contact is going to be increased, so that more friction, that's why machinability problem arises.
In turning operation, the feed rate could be doubled to increase the metal removal rate. Feed rate is F2. If you are rating in terms of F1, that is 2 times of F1. That is what they said to increase the metal removal rate. To keep the same level of surface finish, nose radius of the tool has to be R2 in terms of R1. They are asking, but condition is to keep the same nose radius, same surface finish. So H1 of H max of first condition must be equal to the H max of the second condition. So as per this, if you write H max based on feed and nose radius for the practical plane turning operation, so it will be F1 square by 8 R1 is equal to F2 square by 8 R2. So here F1 square as it is, 8 R1 as it is, instead of f2 you can write it as 2 times of f1 whole power 2. So that will be equal to 4f1 square by 8 r2 as it is. Now f1 square get cancelled, this 8 get cancelled, r2 in terms of r1 if I am writing, so r2 I take on the left side, r1 if you take on the right side, it will be 4r1. Therefore you can say that nose radius is multiple by 4 times as compared to the first condition of the nose radius. Therefore answer for this question is option C. Right. So in this question, if you observe, they said in a typical metal cutting operation using cutting tool of positive rake angle alpha, it is 10 degree. Alpha or alpha naught you can say is 10 degree. It was observed that shear angle phi is equal to 20 degree. The friction angle, beta they are asking. See, by providing two angles, when they are asking third angle, we don't have any other data, then we should take first Ernst and Merchant theory for the minimum power consumption. 2 phi plus beta minus alpha is equal to pi by 2. So here two angles we know and third angle we required. Beta is equal to, shall I say, 90 plus alpha is equal to 10 minus 2 times of beta is phi is equal to 20. 90, this 2 phi will be minus sign and alpha will be plus sign. 100 minus 40 will be a 60 degree. That is what the answer, option C here. So very simple question. And why I am applying this equation? See, not only in this question, this type of any question where when we don't have a sufficient information, so in that case we can use this minimum power consumption condition for the orthogonal machining, or you can say it is the first Ernst and Merchant theory. Based on that we can calculate whatever unknown angle. Most of the time by providing rake angle, either they give shear angle related information and we need a friction angle, or sometimes friction angle related information they will provide where we required a shear angle. But from this we can get that particular conclusion.
A cutting tool has a nose radius of 1.8 mm. So nose radius of 1.8 mm, 8 mm. Feed is for a theoretical rough surface. The feed for theoretical feed is not given. Roughness is given 5 microns, micrometer. Okay, 5 micrometer. So they are asking that feed is nothing but mm for revolution. Feed is nothing but mm for revolution. So here roughness is equal to RF is equal to F by 8R, F square by 8R you can take. So the surface roughness is equal to F square by 8R, and here surface roughness value is given, radius is given, they are asking feed. Okay, so feed is equal to 8R into RF you can take under root, that is equal to under root 8 into radius is 1.8 into RF is equal to 5 into 10 power minus 3, because I am converting micron into mm, so 5 into 10 power minus 3. So if you solve this question, nearly will get 0.268 mm per revolution. 0.268 mm per revolution. So this is a question from the metal cutting. So if you remember this formula, you will guess the answer easily.
In orthogonal machining operation, the chip thickness and the uncut chip thickness are equal to the 0.45. So T1 and T2 both are equal to the 0.45. It means that, shall I say, chip thickness ratio that is equal to T1 by T2 is equal to 1. If the tool rake angle is 0, if alpha is equal to 0 degree, the shear plane angle phi they are asking. So we have one standard equation that is tan phi is equal to, we derive this equation in our theory discussion, tan phi is equal to r cos alpha by 1 minus r sine alpha. So here if you substitute, then we can get directly shear plane angle phi is equal to tan inverse of r is equal to 1 cos 0 by 1 minus 1 into sine 0. Sine 0 is 0, so therefore denominator will be 1. That is the final answer as a tan inverse of 1 valued. So tan phi will be 1 when phi is equal to 45 degrees. So based on this particular approach, as we are getting answer as 45 degree. So very simple question where you just need to remember this equation, how we got this equation for the shear angle calculation. From there we can get the conclusion of a shear plane angle.
What is the approximate percentage change in life? Percentage change in tool life actually. Okay. Percentage change in life T of the tool with the 0 rake angle used in orthogonal cutting, when its clearance angle alpha is changed from 10 degrees to 7 degrees. Okay, 0 rake angle and clearance angle changed from 10 degrees to 7 degrees. Now, flake wear rate is proportional to cot alpha. Hint is given. So, generally remember tool life is proportional to 1 by flank wear rate. Flank wear rate. Okay, if wear rate is more, tool life is going to decrease. Now, here it is given in the question, flank wear rate is proportional to cot alpha. So, flank wear rate is proportional to cot alpha. Flank wear rate is proportional to cot alpha. So, I can write tool life T is proportional to 1 by cot alpha. Tool life T is proportional to 1 by cot alpha. So, from this you can take T2 by, otherwise you can take T2 by T1 is equal to cot alpha 1 by cot alpha 2. Otherwise, tan alpha 1 by tan alpha 2. Tan alpha 1 by tan alpha 2. So, T2 by T1 is equal to, sorry, here it is reverse, tan alpha 2 by tan alpha 1. So, tan 7 degrees by tan 10 degrees. So, here approximately 0.7 you will get. So, T2 is equal to 0.7 times of T1. So, how much it is reduced to life? 30% is decreases. So, tool life is decreased, how much? 30% decreased. So, this is the correct answer for this question. 30% tool life decreased. A conventional lathe and CNC lathe. Remember, there are two lathe machines is considering, conventional lathe and CNC lathe, are under consideration for machining a given part. So he is using two machines to do a machining operation. One is a conventional lathe, second is a CNC lathe. So, the relevant data is shown below. Now, this is the data for conventional lathe, this is the data for CNC lathe. The preparation cost rupees for conventional lathe is 30 and CNC lathe is 150. Production time per part is 30 minutes, 15 minutes. Machine and operator cost is 75 rupees, 120 rupees. The machine preferred for producing 100 pieces is. So, which one is better? Is it conventional lathe or CNC lathe, like that? They are asking. So, you can eliminate C and D out of A and B. Even you will guess the answer without any calculation, because always CNC machine is most efficient. The question is illogical. Directly going to go with the B option. But anyhow, we will calculate the total cost. See, for conventional machine, for conventional lathe machine, total cost is equal to preparation cost 30 plus machining cost you can take 30 minutes is spending. So I am converting into hours. 30 by 60. Okay, 30 by 60. Cost of the operator is 75 rupees per hour. Like that 100 components we are going to make. 100 components we are going to make. So the total cost of this is 3,780, nearly 3,780 rupees. Suppose if I consider CNC machine, CNC lathe machine if I consider, CNC lathe machine if I consider, total cost is equal to preparation cost 150, preparation cost is 150 plus only 15 minutes taken for the production per part. So 15 minutes I am converting into hour. 15 by 60 into 120 rupees is charging operator. Like that 100 components. Now if I add this, if I solve this, I will get the answer. I will get the answer, that is 3150. 3150 rupees. So if we compare the cost, CNC lathe machine cost is lower than the conventional lathe machine. So CNC machine is better than conventional machine. Simple question. CNC machine is lesser than conventional machine.